and welcome friends. In this particular module, I wish to discuss about trigonometrical leveling. Broadly, we'll cover definition, uses, various cases of trigonometrical leveling, and the respective elevation formulae. As you learn the content, you will be able to demonstrate use of theodolite for trigonometrical leveling as a surveying technique under various circumstances. Already you know about the ordinary leveling operation, in which we make use of variety of the levels in order to take the readings on the staff held vertically, which is usually 5 meters in length. But the major limitation there is we cannot have inclined line of sight. That is, we have to have the sights with respect to the horizontal line of sight only. Hence, as we work in broken difficult ground, if there are considerable undulations, then the ordinary leveling will be cumbersome operation. So under such circumstances, we make use of trigonometrical leveling, which essentially employs theodolite. So this particular trigonometrical leveling is an indirect method of leveling in which the difference in elevation of the various stations are determined from the observed vertical angles and the distance measured up to the station under consideration, which could be either directly measured or indirectly determined. This kind of work is commonly used in all kind of topographical survey to find the elevations of various stations such as tops of the buildings, chimneys, churches, etc. Also, this particular method has applicability in plane as well as geodetic surveying. Already you have got acquainted with these two terms. In plane surveys, we deal with horizontal plane. We do not take into account the curvature of the Earth's surface, whereas in geodetic surveying, we have to take into account the curvature of the Earth's surface and we have to reduce the major distances to mean sea level. The discussion pertaining to this particular presentation is for plane surveying only. Let's consider the case 1. Here, as you see, this is certain tower, this is certain feature of which we wish to determine the elevation. Its base is accessible, hence the distance in between the equipment and the base of this particular object can be measured and is expressed as d here. With respect to this particular instrument station, we can carry out all the temporary adjustments like leveling, centering. We can have the leveling operation done with respect to the altitude level tube. As you know, we have to measure the vertical angle, and for that here we have to refer to the altitude level tube. So as we define the horizontal plane with respect to that, we can sight the station F and we can have this theta vertical angle measured with respect to it with both face left as well as face right condition. So average of that particular angle can be expressed as this theta. As such, this h from this triangle CEF can be expressed as d tan theta. Here we can have the backside on certain benchmark in order to determine this particular EHI, or otherwise we can refer to the RL of the instrument station in which we can add the height of that particular equipment in order to work out that particular EHI. Hence, this RL of station F can be expressed as RL of benchmark plus S plus this H. As we work out this H as a d tan theta, RL of F can be worked out as RL of Bm plus S plus d tan theta. So this is the simplest possible case as far as trigonometrical leveling is concerned. As we deal with a variety of the cases, sometimes we may come across with such a site condition in which this particular base of the object is not accessible. So the way you see here, because of some difficulties, this particular capital D we cannot measure directly in between this particular instrument station and the feature under consideration. So under such circumstances, we have set of angles measured with two instrument stations. So the way you see here, this is instrument station say O1, this is instrument station say O2. The distance between them is small d. So here when the equipment is kept at station O1, we can cite the station F the way we did for case 1. Accordingly, this theta 1 can be determined as average angle. Now here we can transit the telescope, have this particular O2 marked at convenient distance d. Again set the equipment, carry out the temporary adjustments. After having the equipment leveled with face left as well as the face right, we will be able to determine this angle theta 2. As you see here, for both these particular instrument stations, we have kept the axis at same level. So as we deal with the first case when the equipment was set at station O1, here this H can be expressed as d tan theta 1, whereas when the equipment is set at O2, this H can be expressed as d plus d tan of theta 2. Hence, as we compare these both expressions, this d can be expressed as d tan theta 2 divided by tan theta 1 minus tan of theta 2. This RL of station F can be determined by making use of backside taken on this particular benchmark. So RL of benchmark plus that S plus H will be nothing but this RL of station F. So here we can make a use of this particular value d tan theta 1, and accordingly the H can be expressed the way we discussed here. With the same site, we can have the solution in different manner, the way we have discussed here. As you see, here both the instrument setups that we defined earlier are not at the same level, but here the instrument axes are set at different levels. With this case, we can keep the instrument height nearer to the station higher as compared to other position, or it could be kept at lower level, and accordingly we can deduce the expression. For this particular case, let's assume that the equipment at O1 has lower HI as compared to the subsequent setup. Say with the first setup, the vertical ordinate with respect to this particular horizontal plane up to the top of that particular feature is say h1, whereas the way we wish to have the subsequent setup at O2, under that particular case, here the vertical ordinate with respect to the horizontal plane up to the top of the feature is say h2. As such, this h1 minus h2 will be equal to s2 minus s1, which are the staff readings taken with the line of sight horizontal on certain point of known elevation, say B here. Hence, h1 minus h2 is equal to s2 minus s1 is equal to say s. So, here the way we considered earlier, from this particular triangle, say O1 dash, A double dash, F, this H1 can be expressed as d tan theta 1. Similarly, from the other equipment setup, the way we refer to triangle O2 dash, A dash, F, this H2 can be expressed as d plus d tan of theta 1. As we subtract this particular expression 2 from expression 1, what we get is h1 minus h2 is equal to d tan theta 1 minus d plus d tan of theta 2. Hence, this s can be expressed as d tan theta 1 minus d tan theta 2 minus d tan of theta 2. Hence, as we solve for this particular capital D, we get this particular expression s plus d tan of theta 2 divided by tan of theta 1 minus tan of theta 2. In order to determine the RL of that particular top station, we can make use of, say, S1, RL of F is equal to RL of benchmark plus S1 plus H1. In a similar manner, we can also make use of this particular S2 in order to determine this, say, RL of F. Obviously, the value should be one and same. We can consider the third case here, wherein the instrument station and the elevated objects are in the same vertical plane. As well, here the instrument axes are at different level. So the way we discussed earlier, here again h1 can be d tan theta 1, h2 will be similarly d plus d tan theta 2. Here we have to deduct that particular h1 from h2, and accordingly this d, when the instrument station at station O1 is higher as compared to the other subsequent setup, we have to make use of this particular expression. The RL of station can be determined the same manner, RL of benchmark plus S1 plus H1. There can be, say, another case for this kind of equipment setup. Say, for example, here we are trying to take the staff reading S1 and S2 held on certain point of known elevation, could be benchmark. Say, here if this particular feature under consideration has got considerable elevation, So under that particular circumstances, it may not be possible to have this S determined by simply taking the difference in between that two stop readings, because here the difference in between two subsequent stations or other instrument setups could be large. So under such circumstances, we can have the intermediate instrument setup established by making use of reduced level of the instrument station that is determined with respect to the benchmark, and we can proceed with the similar calculations. Here, as you see, the base of the object is not accessible. As well, we are not keeping the equipment setup in the same vertical plane. Let's try to understand the procedure that we wish to follow. Let's say the equipment is set at station O1. As such, this dotted line will refer to the horizontal plane passing through the head of the equipment. As such, we can measure theta 1 with respect to station under consideration. Similarly, here with respect to the horizontal line O1 A dash, we can define instrument setup O2 at convenient distance D. As we drive the peg at station O2, we can measure angle alpha, which is nothing but O2 O1 A dash. Now, shift the equipment at station O2. Again, have the temporary adjustments done. The way we measured theta 1 here, let's measure theta 2, that is obtained after sighting this particular station F. Here we can also measure angle beta, which is nothing but A dash O2 O1. So if we consider this particular plane triangle O1 O2 A dash, angle subtended at A dash as theta can be expressed as 180 degrees minus alpha plus beta. So in this particular triangle, we do not have O1 A dash or O2 A dash, but we do have alpha, beta and this T. Hence, as we apply sine rule to it, we get O2 A dash by sine alpha should be equal to O1 A dash by sine beta should be equal to O1 O2 by sine theta. So, as you have the value O1 O2 as well as you have determined this particular theta, you can determine this O2 A dash as well as O1 A dash, which is nothing but the distance between the instrument setup and the base of the feature under consideration. So here, as we have set the equipment at O1, we can have this particular H1 expressed as distance A double dash F, which is in turn A double dash O dash tan theta 1, which is nothing but A dash O1 tan theta 1. Similarly, here this H2 is nothing but A1 O2 tan of theta 2. Here the way we deduced earlier, V is equal to tan of theta is the similar approach. So, having this particular H1 as well as this H2 worked out, now this RL of F can be determined as, say, RL of benchmark plus this S1 plus H1 if the instrument setup O1 is considered. If we consider other setup, RL of benchmark plus S2 plus that H2 will give us the RL of the station F. As such, whenever the both equipment setup are not in the same vertical plane, we can determine the distance in between the instrument setup and the feature under consideration or its base indirectly. We can make use of trigonometry to work out that particular H1 and H2, and hence we can determine RL of the feature under consideration. So friends, thank you for your attention. I hope the various cases that I discussed here are clear to you. So in the coming presentation, we will discuss about theodolite traversing. Until then, I wish you very happy learning. Thank you.